Testing. Hello, class. Today we're going to do the first part of section 11.2. I'm assigning the problems for 11.2 today, April 22. They'll be due April 27. There'll be two parts to this, but what we cover today will be enough to get you through that assignment. So assigned 11.2 today, April 22, due April 27. This chapter is about analysis of variance, called an ANOVA test. We looked at this the last time we met. Basically, it's a type of hypothesis test for 3 or more populations. So far, we've been working with either a single population or 2, but now we're looking at 3 or more. When we're looking at 3 or more means, we said that our null and alternative are always going to be of this form. The null will be however many populations we're dealing with, 3, 4, 5, whatever. We start off assuming that the mean for each population is the same. The alternative is that at least 2 of them differ. That's always going to be the case, so look for that as we go through these tests. We also covered last time that the statistic that we use is not a T or a Z, but we get a new statistic, an F. That is also going to be a ratio. That's not new to us, but it's a ratio that describes the variance between means divided by the variance among the individual samples. We also talked about last time that we're going to get a ANOVA summary table. This will be printed out for us, and we have to be able to pull it apart. Our F statistic has MST, which is this quantity divided by K minus 1. The F statistic denominator is this quantity, which is the SSE divided by N minus K. Kind of complicated looking, but also keep in mind K here refers to the number of groups or number of populations. N, located here, or here, is the total number of data points. That means that our degrees of freedom has 2 parts to it, like an ordered pair. This being the first one, this being the second one. That'll make a little more sense once we get into an example. I want to show this one again just simply because it gives our degrees of freedom as an ordered pair. If you don't have that copied down, you probably should. Also, I'd like you to be aware of that we have a table of F values, page 642 to 645 in your book. I'll be showing a copy of that, so you won't need your book yet today, but when you're doing your assignment, you might in some cases. Let's now take an example of what we're talking about. The length of time spent in an examination room is recorded for each patient seen by one of 4 physicians at an orthopedic clinic. Does the data given on the following slide give evidence that is statistically significant for a difference between the mean times, the average times, each doctor spends with an individual patient at an alpha level of 0.05. Assume we have normal populations. Run a critical value test comparing these multiple means. First of all, why is it a multiple mean? Because I have 4 physicians. What we're really testing is, does each physician devote, on the average, the same amount of time per patient? Or does one or more of them give more time per patient? Believe me, medical facilities around the country take note of this. So here's the data. Keep in mind, remember, I'm running at an alpha level of 0.05. I'll come back to that. Here's the data. Physician 1 apparently met 1, 2, 3, 4, 5, 6, 7 patients that day. And the first patient, there was 34 minutes for that patient, 25 minutes for the second, etc. Physician 2 spent these amount of times. Physician 3 met more patients. It doesn't necessarily mean that he spent less or more time, or she did. Physician 4 also had this many visits. We're given that summary table right here. The F statistic is 3.5. Okay? Remember that F statistic as well. I'll come back to that in a moment. But now let's run through the test. Probably would be good for you to copy this format down. It's going to be very similar to what we had, but a few slight changes. Remember, we said the null and alternative are always the same, other than it might be 3, might be 4, might be 5. The alternative is always the same. So here's step number 1 of our critical value test. Remember, we were testing at 0.05. We're comparing multiple means, and that's why we tell our readers we're using the F statistic. Previous tests, we would do something like n equals 40, z-test, or n equals 10, t-test, or t-statistic. Whenever we're comparing multiple means, we use an F statistic, no matter what the size of the samples were. Sometimes we're going to have to get this critical value from one of the charts. So I'd like us to look at that once right now. Here I listed it for you, but let me show you where we got it. First of all, our degrees of freedom, you remember, was k minus 1 and n minus k. K, there were 1, 2, 3, 4. So 4 minus 1 gives us 3 for the first coordinate, so to speak. The second one is n. And apparently, if you go back and you add up all the data points, 1, 2, 3, 4, 5, 6, 7, count them all up, you end up with 28 data points. Minus k, which was the number of groups, gives us 324. We need to find the chart, because each chart has a different alpha value. We have alpha values given on this set of charts from page 642 to 645, alpha levels of 10%, 5%, 2.5%, and 1%. We're looking at 5. Remember, our degrees of freedom are 324. So here's an alpha table, just like the one in the back of your book. Remember, our degrees of freedom was 3, so I find the 3 in the top, and was 24. So I'm going to go 3 down to 24. That gives us 3.0088. I rounded it off to 3.01. Remember again how I got that. My degrees of freedom was 324. Got to find the correct alpha, 5%, 324. I rounded it off to 3.01. 3.01 is my rejection region. It's my line in the sand. First of all, something you need to be aware of the F distribution. It is not symmetric. The F distribution looks like this. It is skewed right. The 1 is about in here someplace. Remember, we said if F is close to 1, it's within reasonable variance. Our line in the sand was at 3. So this becomes my rejection region. If it goes to the right of 3, if F is greater than that 3.01, that's my rejection region. You will never have a two-tailed test for an ANOVA like this. It's always a single tailed because it's not symmetric. It's not symmetric. The F statistic will be given in your computer printout. You remember it was given right here at 3.5. So I simply write it down. I compare that to the line in the sand, to my rejection region. It went over the line. So that meant I had sufficient evidence to reject the null. And now I conclude this in context, at least 2 physicians have different mean times that they spend with their patients. That's the conclusion of our test. We're concluding not all the doctors spend the same amount of time. Okay? Again, if you need to pause this and copy it down, please do so, because you're going to be expected to pull these off on the final. Okay? And you could have a test very similar to this, or whatever the test is, it will have, again, these 4 steps. They should look fairly familiar to what you've seen. Let's take another example. USGA wants to compare the average distance, the mean distances associated with 4 brands of golf balls. So they use a robot to hit these golf balls. They call the robot Iron Byron. The idea is they want to see the distances. Do certain brands naturally go a greater distance than other brands of golf balls? They choose a random independent sample of 10 from each brand. And they have their robot strike that sample of 10, and they record the distances of each drive. We run the test to compare the average distance for each brand. This time we're using alpha at 10%. Results are shown in the following table. Okay, well, I'm going to put that right over top here. Here's brand A. Here were the 10 distances. The robot hit 10 balls and they went those distances. Had an average of 250. That would of course be in yards. And the variance was 22. Standard deviation would be around the square root of that, which would be about 4 point something. Brand B had an average of 261. Brand C, 269. Brand D had an average of 249. They're obviously not all the same. But the question is, are they different enough? Do we have mathematical evidence to say one brand is better than another? You would be given a summary table. The summary table is right down here. This particular table also reprinted brand A with its average, brand B with its average, C with its average, and D. Told you again there were 40 total golf balls hit. There are 4 groups. So looking at this, K is equal to 4. N is going to be these added up, which is 40. So now my degrees of freedom, K minus 1 and N minus K. K minus 1 is 4 minus 3, 4 minus 1, which is 3. N is 40 minus 4, which is 36. That would be to my degrees of freedom if I needed to look it up on the chart. They printed out pretty good summary table right here. Notice they give me the F value. They gave me the P value. Notice it's exponent negative 12. That means the exponent right here between 3 and 9 would be moved to the left 12 positions. The line in the sand, my rejection region, that's F critical. That line in the sand is 2.24. We'll remember all those details as we're going through. But now let's run the test. Our mean is referring to the distance by each brand. Again, I begin the same old way. I assume all of them start off equal. I'm hoping to see if there is evidence that at least 2 of them differ. The problem told us to use alpha at 10%. Our next line is to tell the reader we're comparing multiple means, and that's the reason why we're using the F statistic. F critical 2.24 came from that summary table. So that's why I called that my rejection region. You also could have looked it up on one of the charts in the back. Remember again, you would have had degrees of freedom 336. That means that you would have gone 336 over 3 down 36. You would have gotten 2.24. The F statistic, again, you recall, was given in the printout. All I do is copy it down, and now I make the conclusion. There's no doubt it's past my rejection point line in the sand, so I have sufficient evidence to reject the null, conclude that there are at least 2 brands of golf balls that have different means. Again, if you need to pause it, copy all that down, do so. After you do it, copy it down 2 or 3 times, it'll begin to be automatic for you. Okay? Some things that are different. The alternative and the null are different. The alpha level is always given in the problem. The fact that we're comparing multiple means using an F statistic is different. We have a rejection region, which is the same, but we have to get it off of another chart. This is given, same type of conclusion. The underlying parts are what are different with this ANOVA test. Yet another example. Sales of People's Magazine are compared over a 5-week period at 4 outlets. 4 outlets. Show the test to determine, does the data on the following slide give evidence that is statistically significant to indicate a difference in the mean weekly sales, alpha at 5%. Here are the 4 stores. The mean weekly sales, apparently store 1 sold 102 of the magazines, 106, 105, 115, 112. Store 3, store 4, and 5. We're looking to indicate a difference in the average weekly sales. Week 1 was 102, week 2 was 106. Over here, week 1 is 89, week 2 is 91, etc. Alpha 0.05. That should be a decimal over here. I apologize. Decimal in the wrong place. Here's my summary table. Notice they give me a critical value. That's my rejection region. They give me a p-value between 1 and 2.5. They give me my F statistic. So I'm ready to go with my test. Identify what mu is referring to. It's the average weekly sales. I start off by letting them all equal each other. If there were 3 of them, I would have had just that. There were 5 of them, I would have had 1 more here. Some of the problems in your book might have 5 or 3 or something. They won't all have 4. And at least 2 means differ. Alpha at 5%. I tell the audience I'm comparing multiple means. That's why I'm using an F statistic. This rejection region, 3.24, either I would get it from the chart if it wasn't given in the back of the book. Let's again just check that chart out once. Degrees of freedom, 4 groups minus 1 is 3. I had 20 scores minus 4, that's n minus k. 20 minus 4 is 16. At alpha at 5%, I'm going to go 316. Alpha at 5%, go to 3 down to 16. Right there it is. I rounded it off to 2 decimal places, 3.24. I could have gotten that off the chart or off the printout. The printout, you remember, also gave me the critical value 3.24. The F statistic was given on the printout. Make sure that you know where that came from. Right here is the F value, 4.26. That is over my line. It's in the rejection region, sufficient evidence to reject, and I'll conclude there are at least 2 stores that have different weekly sales. Gave you 3 examples here. Hoping after 3 of them, these become pretty standard procedure for you. The good part is that they print out most of it in some type of computer tab printout. It's a matter of you taking that printout, putting it in an organized form that fits the hypothesis test, make the proper conclusions, etc. That is all I have for today. Another fairly short lecture. Assignment is 11.2. I believe you got to run 3 of these tests for 11.2. We'll also do some more work with 11.2 yet on Friday. We will see you then.